Welcome to this lecture. In today's lecture, we are going to talk about some applications of mean value theorem. So essentially what we are doing is this. Let us just do a small revision. We had this equation, Laplacian of u equals to 0. Yeah. This is just a simple harmonic, this is called a Laplace equation. The solutions are called harmonic functions, right? So let's say this is in omega and u restricted to the boundary is, some function g. Yeah. Now the question was this. So the question was, is it well posed? Yeah. Or maybe I can do a more general problem. Let's say I take a Poisson equation. Okay. Let's say this is f. Now the question is one well posed? Well posed. Okay. Now you have, I think, more or less some idea of what to do. See, essentially, let's say this omega can be any omega, right? I mean, it may not be a particularly a rectangle or a circle or a sphere, that sort of thing. So not a very nice. So if, let me put it this way, if omega is not a nice domain, yeah, you do understand what I mean by nice. So the usual domains, okay, not a nice domain, okay. Then what happens? Separation of variables fails, yeah, okay. So essentially, I give you a crazy looking domain, right? I mean something like this. Let's say something like this. Separation of variable. You can't use separation of variable here, right? So what do you do then? Let's see. The point is this. For this sort of domain, okay, but I mean for there are most of the domains which you can think of, separation of variable won't work. And essentially, what do you do in those cases? In those cases, we rely on your qualitative analysis. Okay, qualitative analysis. So let me give you a small remark here. See, I mean, you may have heard that Green's function, you can actually construct a Green's function and you can use it to solve this sort of Poisson equation, right? Yeah. So this is called the Poisson equation, if you remember. Okay. And so you may have heard about it. We didn't talk about it in this course, but you may have heard that there are functions called Green's functions which you can use to solve this problem. Of course, there are. Okay. And for an arbitrary domain, I mean, not any arbitrary domain, but I mean, smooth arbitrary domain. We will talk about it later, what sort of domains we can. But for generally, for most of the domains, we can actually construct a Green's function. I mean, you can show that there exists Green's function which solves the Poisson equation. That can be done. Yeah. The problem is this, that Green's function, you can only show that it exists. Yeah. You cannot actually find an explicit function. So here also the same thing is happening. You cannot find an explicit, solution of this equation in any case. So what do you do then? So in this case, what we were doing, without solving the equation, we were trying to find some properties of this solution. So let's say this problem has some solutions. Okay, I want to find some properties of the solution. We have seen, what are the properties we have seen till now? Properties. We have seen that this one admits a unique solution, right? Admits an unique solution provided it exists. It exists. Okay. So you see, essentially, we did not prove that there are solutions, but if you can show that there are solutions, then we have showed that the problem admits a unique solution. This you remember we did in the earlier week. Okay. And moreover, for this problem, for Laplacian u equals to 0. So basically harmonic functions. If a function is harmonic, okay, so any solution of this equation, okay, what does it do? It satisfies this, right? Mean value property. So over bxr u of y dy. Please do not underestimate this property. This is probably the most fundamental property you can think of some particular class of functions. Okay, so u of z dz. Okay, So this is the mean value property. This we have proved last class. So now what we are going to do is I am going to show you some more properties of this harmonic function. See, once you understand harmonic functions, Poisson equation, dealing with Poisson equation is much easier. Okay, so we will only concentrate on harmonic function for now. So what we are doing is we are going to prove some property of harmonic functions. Okay, if you remember what are harmonic functions, these are functions for which Laplacian of u is equals to 0. Okay, so properties of harmonic function. So the first important property, very important property, is called the strong maximum principle. Strong maximum principle. Okay, so what it says is this. It says that suppose u is in C2 omega intersection C omega bar. Okay, so what we are doing is we are saying that the function, let's say that's your omega. Okay, that's your omega where we are talking about, and so essentially here Laplacian of u is 0. So we are looking for properties of u. See, we haven't solved this problem. Yeah, of course you can find some solutions, but not everyone. But the point is this: let's say any u is there which is in this, Laplacian, which satisfies Laplacian u equals to 0. I am writing down some properties of those in some domain. Yeah? So let's say that's your omega. Now we are using u to be C2. So inside the double derivative exists and they are continuous inside. Okay. And what about on the boundary? Boundary double derivative may not exist, but boundary it actually coincides with a continuous function, right? C omega bar. So let's say this is harmonic within omega. Clear? So this is what we are assuming. Okay. Now, okay, let me give you this and then we'll talk about that, the remark. First of all, what happens is, if this happens, you can say that the maximum of u over omega bar equals to the maximum of u over the boundary. Clear? And number two, what you can do is you can show that if there exists x naught in omega such that u of x naught is equals to the maximum of u over omega bar. Okay, so essentially what it is saying is, if the maximum of u is attained anywhere in the interior of the domain, then u is constant. Here, then u is constant provided omega is connected. Clear? Okay. So what exactly is it saying? Let us understand first the theorem. This is a very important theorem. The proof is not very difficult once you prove the mean value property. But let us understand what is the thing. It is saying, see in the first assumption, we haven't assumed that omega is connected. Okay, we did not assume that. Okay, so what we are saying is the maximum of u over omega bar is equal to maximum of u over the boundary. So basically what it is saying is the maximum u attains in maximum on the boundary. It is, see, the first thing, note property 1 implies the maximum is attained on the boundary. Okay, see, property 1 does not say anything about the interior. It may happen that it is also, there is a point where in the interior also it is taking maximum, but you can always guarantee that there is a point. Okay, see, 1 is not saying that it cannot attain the maximum in the interior. Please understand this. Yeah, it is saying that you can always find a point on the boundary of the domain where the maximum is attained. That is what it is saying. Yeah, it may very well be happening. So say it does not imply that the maximum is not attained in the interior. Okay, so it is not saying that the maximum cannot be attained in the interior. It may be, but it is saying that I mean, we don't know whether that happens or not. All we know is it is always attaining on the boundary. So this is the first property. Note the second property is, this is very important. Yes, here I did not assume anything on omega. Okay, so important thing. So let me put it. I don't know. Maybe let us put it in white. Omega is open and bounded domain in Rn. Okay, here see, please understand, for a strong maximum principle to hold, this has to be open and bounded. This is very important. Why? Because you see, if it is open, omega bar is closed, right? And it is a bounded domain. So basically, you are looking at a continuous function on a closed bounded domain, which is a compact set. So continuous function on a compact set attains its maxima. So that is why this maxima is there. Do you understand what I'm saying? See, please, I mean, try to understand this thing. Without this condition, this is very important. Okay, this condition, you cannot guarantee that this happens, because you cannot even guarantee that the maximum is attained. Okay, so let me put it this way: without the boundedness of omega, without the boundedness of omega, the property does not hold. Okay, so that is true. Okay, now let us give you an example. Yeah, let me give you an example. The problem. Okay, before that, there is another property which we want to talk about, number 3. See, here I am saying the maximum is attained on the boundary, right? That is what I'm saying. I'm not saying it is not attaining on the interior. I'm still talking about 1. Okay, you can also say that the minimum, see, u is a continuous function. U is a continuous function on a closed bounded set, right? Omega is open, omega bar is closed, right? So it is a continuous function on a closed and bounded domain. So it attains the maxima and the minima. Now the question is this: if the maxima is attained on the boundary, where does the minima is attained? So the minimum of u over omega bar on the whole domain, including the boundary omega bar, is attaining on minimum of u over the boundary. Okay, this is also true. So what you can say is the maxima and the minima is always attained on the boundary. How do you prove it? Just replace u with minus u. Okay, see, u satisfies the harmonic function equation, the Laplace equation. So minus u also satisfies the Laplace equation. It's Laplace equation, the space of solutions are it's a vector space, right? So minus u will also satisfy this, and you can just replace u with minus u, and you can say that the maximum can be replaced with the minimum. Okay, now number 2. This is what is so important about the property 2. Okay, property 2 is important because what it says is this: it connects the whole thing. So it is saying that once you understand that omega is connected, see, most of the time, so please remember this thing, I am not going to repeat this again. In this course essentially, we always assume omega is connected. Okay, this is always assumed, but generally, I mean, why? So you may ask that why I am putting these two conditions separately. See, this condition, the second property, what does it say? It says that if there is a maximum, if a maximum is attained in the interior, what it is saying is this. See, in the earlier case, it is saying that the maximum is attained on the boundary. It does not say anything about the interior. It may or may not happen on the interior. In the second property, it is saying that if there is a point where the maximum is attained, right, then the function has to be constant. Clear? And this is true if the domain is connected. Okay. But for our course, we are always assuming omega is connected. Okay. So for our course, we will always assume that the omega is connected. So basically, hence the strong maximal principle, I will write it like this: SMP, strong maximal principle. Okay. SMP implies that the maximum of a harmonic function can only be attained on the boundary of the domain. Okay, boundary of omega. So clear? Is this clear? See, unless the function is constant. Is this clear? So what it is saying? It is saying that, see, it is saying that if the maxima is attained on the somewhere in the interior, then the function is constant provided omega is connected. Now in our course, we are always assuming omega is connected. Okay, so connected or not, you always know that there is a maxima on the boundary, and here it is saying if there is an interior point where the maximum is attained, then it is constant. So you can plug these two together and you can say that the maximum of a harmonic function, okay, the maximum of a harmonic function can only be attained on the boundary of the domain until unless the function is constant. So basically, if you just throw away the constant functions, all other harmonic functions have to attain. So basically, it says, let me put it this: if you throw away the constant harmonic functions, okay, constant harmonic functions, then all others attain its maxima / minima, okay, on the boundary. I hope this is clear. Yes. And you may think that I am taking too much time explaining this thing. This is the most fundamental property of PDEs. So see, mean value property is such a property which is always only satisfied by harmonic functions. Okay, this maximal principle we are proving maximal principle using mean value theorem, but maximal principle can be used. Okay, you can find maximal principles not only in Laplace equation but also heat equation and heat equation also. Okay, so let us write it down, and many other partial differential equations. So this is a very important property. Okay, so this is a very, very fundamental property. Let me put it in a star kind of thing. This is a star property. Let's just put it like this. Very, very important. Please remember this thing. So this is strong maximal principle. Here we are just doing it for a Laplace equation. Later we will do it for a heat equation also. Okay, but for heat equation we won't do any. I mean, not exactly the mean value property which we did. So let us look at the proof of this thing. Proof. What is the proof of this thing? The proof is very easy. So let us assume that. So we are we are not really interested in all this. Omega is not connected. No, omega is connected. So we assume omega is connected. Clear? Okay, omega is connected, and hence if omega is connected, what we are going to do is we'll assume let x naught is in omega with u of x naught, with u at the point x naught is m, okay, which is given by the maximum of u over omega bar. Clear? So basically what we are saying is there is a point in the interior. So essentially what do you have to show? I just have to show that, see, u is a continuous function on omega bar. So definitely u attains its maxima, right? Maxima and a minima is always attained somewhere. Either it is on the boundary or in the interior. We just have to show it does not attend in the interior, that's all. And then definitely it has to be on the boundary, right? Okay, so let's just assume that there is a point x naught where it is taking the maxima. So the maximum of u over omega bar is m, where u of x naught is, yeah, that's the value of u at the point x naught. Now what we are going to do is you set, okay, r, which is basically between you see, what we are going to do is something like this. Let's say x naught is some point here. Okay, the distance between x naught and boundary is this one. Yeah, and we are choosing a r which is like smaller than this. So basically, you can choose r like d by 2. Let's say, yeah, you can do that. So basically, that's your r. So I'm choosing a small ball. So essentially, that ball will be on the domain like this. Yeah. So if that happens, the mean value property says m, this is equals to u of x naught, clear? That is what we have assumed, and that is equals to integral over b x naught r, okay, u of y dy. See, u is a harmonic function, right? This holds for harmonic functions. We want to show that the strong maximal principle holds for harmonic functions. So you see, u of y dy on a ball b x naught r, any ball. Here r is very small. You don't realize this thing, yeah. And that is equals to u at the point x naught. This is mean value property, right? Mean value property. Okay, and this, what happens? See, what is the value of u on this ball? So the maximum of u is always m. I mean, I don't care whether it is this ball or some other ball. It is always m. So I can always dominate it is with m times bx naught r dy, right? This we can always do. So what is it? This is m, and this is 1 by the volume of bxr. So I will just write it like this. Okay, for all you guys, whoever, I mean, for if you guys know measure theory, essentially this is the measure of the ball. Okay, if you do not know, don't worry about it. Just think of this as the volume of the ball. So when you do it like this, it is just 1 by the volume of ball, and integral of dy, that is just the volume of the bx naught r, right? So this gets cancelled out, and this is equals to m. Clear? So this is clear. So now what we are getting is this. See, we are going to get from here that the integral of u over this ball, this is equals to m and less than equals to m, right? Does this, so basically you see, and this equality, when does it hold? So equality holds only if u equals to m, right? Within bx naught r. Clear? Yeah. See, if there is a point where u is less than m, then this, I mean, you can please show this. You can actually dominate that thing with this thing. So basically, this will be greater than equal that m minus epsilon, let's say. Yeah, and the measure of the ball. So I mean, this cannot happen. You cannot show this is equals to m. Yeah. So please check this part. That holds in only if u is equals to m within bxr. So hence u of y is equals to m for all y in bx naught r. Is this clear? Okay. So please check that u is equals to m. U has to be equals to m. So you can show that there are no points where u is less than m. So let's say there are, I mean, for some epsilon, u is m minus epsilon on this ball. Okay, you can actually dominate that. I mean, you can use this thing to dominate that particular thing. So basically, this will be greater than m minus epsilon times that whole thing. So you please do that part, and you can show that it cannot be equals to m in that case. Yes. So u of y equals to m. This is clear. Now what is happening is this. So therefore, the set x in omega such that u of x equals to m. Okay, this set is both open and relatively closed in omega. Okay, let me explain what I mean by this thing. When I say it is relatively closed, of course this u is a closed set, right? Sorry, u is a continuous function, and we are just basically looking at the values of u, level set of u for the height m. Okay, so this is basically in its own right a closed set in Rn. Okay, it's a closed set in Rn. But at the intersection of, I mean, it is relatively close because it is basically we are looking with the intersection of omega, this set. Okay, so that is why it is relatively closed in omega. And why it is open? Because we have showed that if you take a point there inside this set, then you can always have a ball, okay, of radius r where u is m. Yes, so that is why it is open. So basically, you see here, therefore, for a connected domain, omega, okay, we constructed, let's say this set, this S, let's call it S. S such that S is non-empty. Of course it is, because we have assumed that there is a point where the interior where this is happening. Okay, see, we have assumed that there is a point x naught where m is attained. Okay, so essentially this x naught point is always in S. Okay, x naught is always in S, such that this happens, and S is both open and relatively closed in omega, right? So all of this is happening, and since omega is connected, what can you say? This will imply that S is equals to omega, right? Because you guys already know that in a connected domain, if you have a subset which is both open and closed, then the subset has to be either phi or the whole set. It cannot be phi, so it has to be the whole set omega. Clear? So hence there cannot exist a point x naught in omega such that the maximum of u. Okay. So basically, what we have showed that S is essentially omega. So basically, we showed that it is. Omega is a. You see, we proved the second part. We proved that if the maximum is attained on in an interior, then it has to be constant, right? That is what he showed. S equals to omega, it has to be constant. So basically, u is equals to m on the whole domain omega. Okay. So maximum of u there does not. So basically, we showed that there does not exist x naught is omega such that maximum of u is attained at x naught unless u is constant. Clear? Okay. So now, so this is very good. So we learned this thing. As I have again explained, that this is also true if we assume that if we replace maxima with a minimum. Okay, so the same thing happens. Right. Now let me make a small remark here. Okay, maximum principle does not hold. See, whenever I say maximal principle, there is nothing maximum here. You can call it a minimum principle also. Okay, same thing. Maximum principle does not hold if omega is unbounded. Okay. So basically, of course, maximum may or may not be attained. That is one point. Even though maximum may be attained, then also it may not hold. Okay. So you guys have to check this part. It's a very simple example. Yeah, take the exterior of the domain. So I will give you some hint. Yeah, I could have gave you the example, but I want you to do it yourself. Hint: take omega to be the exterior of the domain x square plus y square less than 1, the complement of this thing. Okay, take that to be your omega. Okay, so essentially what am I doing? I am taking the exterior of the unit ball. Okay, so basically this is exterior of the unit ball. Exterior of the unit ball. Okay, that's your domain. Now you choose a function. Yeah, choose a function, a harmonic function. Now choose a harmonic function. Harmonic function, of course not a constant. Yeah, harmonic function in omega to show maximum, strong maximal principle does not hold. Does not hold. Okay, please do it yourself. Find a harmonic function. Okay, which does not, for which, I mean, there will be a similar problem in assignment like this, but I mean, when you are doing this thing, please try to find it. Okay, now let me give you another property of harmonic function. So basically now we are going to use this maximal principle to show some other properties. So properties. Okay, see, this property is called positivity. So what does it say? It says that if U is in C omega bar intersection C2 omega, okay, and satisfies Laplacian U equals to 0 in omega and U equals to G, okay, on the boundary. Let's say this satisfies this. So basically you are looking at a Laplace equation, yeah, but on the boundary it is G, okay, where G is greater than equals 0. Clear? Okay, then you can say U is positive everywhere in omega if G is positive somewhere on the boundary. Clear? So what it is saying is this. See, this is a very easy property. It says that you look at a Laplace equation and U equals to G on the boundary. Yeah. Of course, it is given that G is greater than equals 0. Yeah. What it is saying is this. Please realize this thing. You take a point. If you can show that there is one point on the boundary where G is positive. Yeah. It is saying that just showing one point on the boundary where G is positive is enough to show that U is positive everywhere in omega. So this is a very important property. You realize this thing. Yeah. How can you do that? I mean, take 5 seconds. Think about it. Okay. So I think most of you have got it. So let me give you a short proof. I mean, there is nothing to prove actually, but still. So let us look at the proof of this theorem. What does it take to prove this thing? So essentially, you see, since this is a harmonic function, harmonic functions attains its maxima / minima on the boundary. That is what we learned. Boundary, right? Now G is greater than equals 0. So basically U of x, yeah, for all x on the closure of omega, U of x is greater than equals to the minimum of U on the boundary del omega, which is definitely true because you see U of x is always greater than equal the minimum of U over omega bar, right? And that is essentially minimum of U over the boundary because the maximum is always attained in the on the boundary. This is using the first property. Okay, so now this is equals to the minimum of del omega over g, because u is g on the boundary, right? So, and g is always greater than equal 0. So, the minimum of a non-negative function is always non-negative, right? So, u of x here, therefore, hence u is non-negative, negative in omega bar. Yeah. Now we have to show that if g is positive somewhere, u is positive everywhere. So let there exist x naught such that u of x naught is 0 in omega. Okay. So x naught in omega such that this is 0. Okay. See, essentially what am I doing is this. I have to show that u is always strictly greater than 0 in omega. So this is what, we have to show that u of x is strictly greater than 0 in omega, right? This is what we need to show. So let's say there is a point x naught where u of x is equals to 0. Yeah, if that happens, then what you can say is this. Then you see u of x is always greater than equal 0 in omega bar, and there is a point where u is taking 0 in the interior. So then u attains its minimum at an interior point, right? Interior point. So this is contrapositive statement. We are assuming that if u is, see, we have to show u is greater than equal to 0. Let's say there is a point x naught in omega where u is equals to 0. Yeah, if that happens, then since u is non-negative, it means that u is attaining its minima, which is 0, at an interior point x naught. Okay, what does that? Therefore, strong maximal principle that will imply u is constant in omega bar, right? That is what strong maximal principle says in that case. Okay, so u is constant in omega bar, but that is not true since that can't be true. Okay, but that can't be true. Let me put it this way. Can't be true since g of x is greater than 0. Okay, let's say g of x1 is greater than 0 for some x1 in the boundary. You see, what is happening is this. We already know that g is positive somewhere on the boundary. So let's say there is a point x1 where g is greater than 0, strictly greater than 0. Now, if g is strictly greater than 0 at point x1 on the boundary, okay, so why? Because if g is strictly greater than 0 on the boundary x1, then u at the point x1 is g at the point x1, because u and g are same on the boundary. Okay, so this is strictly greater than 0. You are saying that u is constant on omega. Here, u is constant along in omega bar. There is a point on the boundary where u is positive. Okay, so u has to be positive everywhere. But again, you showed that on the there is a point on x1 where u is 0. Okay, so that's a contradiction. Is it clear? See, what we did is this. Let me explain again. We have to show that this is positive everywhere in omega, right? Strictly positive. Let's say that there is a point where u of x naught is 0 in the interior of the domain. Yeah, right. If that happens, strong maximal principle says what? That it has to be constant in omega bar. If it is constant in omega bar, our condition is there is a point x1 on the boundary where g is positive. Yeah, if that happens, what happens at the to u at the point x1? It is basically g at the point x1, which is positive. So basically, you showed a point x1 on the boundary where u is positive, and you have showed a point x naught in the interior where u is 0. Okay. So, but you are always, strong maximal principle is saying that u is constant in omega bar. Yeah. So that cannot happen, right? A constant function cannot take 0 and 1, 0 at some point and 1 at that point. Hence, a contradiction. Hence, a contradiction. I hope this is fine. Contradiction. Okay. And so we have proved that if G is positive somewhere at one point, then U is positive everywhere. Yeah, very, very important theorem. So another very important property is the uniqueness. Uniqueness of solution to Poisson equation. See here what I am doing is this. So this is property 2. Okay, that's your property 2. This uniqueness of solution for the Poisson equation, what I mean by this is, let's say you are given this equation in omega and U equals to G on the boundary. Okay, of course, where F and G are smooth. Let's just assume that. So basically infinitely differentiable. Let's just assume this thing. We want to show that if U1 and U2 are two solutions, distinct solutions or different solutions to one, then U1 is equivalent to U2 in omega. Clear? Okay. So if you remember last in one of the lectures, we have already covered this thing, that there is a unique solution for this problem. But now we will do it again in a very, we proved it earlier using integration by parts. Here we will use the Maxwell principle to prove it. So let's say, so you define, this is just an application of Maxwell principle, that's all, nothing else. So you just define phi to be U1 minus U2. Okay, clearly phi is smooth. Okay, and so phi is C2 in this case. Yeah, if U1 and U2 are C2, phi is C2, and it satisfies. This is AND. Okay, this is AND. It satisfies. So let's say, let me put it like minus Laplacian. It looks nice. It's just a technical thing, no problem. You can just use Laplacian also. Okay, but it satisfies minus Laplacian of phi is 0 in omega and phi equals to 0 on the boundary. I hope this is fine. Okay, so if phi is equals to U1 minus U2, U1 and U2 both satisfies this equation. So the difference of those two will also satisfy this equation because of the linearity of harmonic functions. Yeah. Now, if that happens, therefore, phi is harmonic in omega, right? See, here what is happening is these functions are not harmonic. This is not a harmonic function. But since I am taking the difference of those two, the difference is harmonic, right? Okay, so phi is harmonic function such that phi is 0 on the boundary. Yeah. So what do we hence by strong maximal principle we have, okay, one thing, again I am saying this thing again and again, we will always assume omega is open, bounded and connected. Okay, this is always assumed. Okay, in this course we are always going to assume this thing, omega is open, bounded and connected. So by strong maximal principle, what do you have? You have the minimum of U over del omega is less than equal, so over omega bar actually, but then that is also on the del omega. Okay, so this is U of x. U of x is always lies between this, right? Maximum of U over the boundary. I hope this is fine. See, U is always in between the maximum and the minimum of U over. So this holds for all x in omega bar, right? So maximum, if you just replace this thing with omega bar, this thing with omega bar, so U of x lies between the minimum of U over omega bar and the maximum of U over omega bar. Yeah, strong maximum principle says that the minimum of U over omega bar is on the boundary, and again the maximum is also on the boundary. So Uf lies between minimum of U over the boundary and the maximum of U over the boundary. Okay, so what is the minimum? So this means that this is basically minimum of phi over del omega less than equal. I think it is already done, right? So maximum of phi over del omega, right? Because u is phi on the del omega. Now you see phi is identically equals to 0 on the boundary. So this is less than equal u. Sorry, I have to change. This is not u. I have to do it for phi. I'm sorry for this thing. This is phi. Phi is harmonic. So this is phi of x. Maximum of phi. Okay. So this is again phi and that is phi. Okay. So what does it mean? It means that phi of x, put it this way. It means that phi of x is greater than equal to 0 and again it is less than equal to 0. So that will give you phi x is identically equals to 0 for all x on the closure of omega. Okay. And there hence u1 is identically equals to 0 is identically equals to u2 in omega bar, and uniqueness follows. Okay. So why I gave you this application of this strong maximal principle, uniqueness, because we already did uniqueness, but again I am doing it because I want you to understand that for other problems also, see, most of the times the method which I showed you using integration by parts showing uniqueness, that may or may not work. You understand what I'm saying? That may or may not work all the time. Maximal principle, if for some operator, for some particular equation, if you can show maximal principle, then I mean there's a good chance that this sort of equation will hold. Okay, I mean you can actually talk about the uniqueness provided the function is linear. Okay, function means the operator is linear. Okay, right. Let me give you another very important property, number 3. So the stability under perturbation. Okay, what stability under perturbation says is this. Let's say you have this equation, yeah, in omega and u equals to g on the boundary. Okay, so this is the equation which we already have. Yeah, so let's say you have a phenomena which you have somehow modeled and you have got something like this. Yeah, and let's say while measuring the next time again you are doing the same thing. I mean you guys know that experiments have to be carried out many times in order to get a reliable data. Right. So even you are doing the same experiment, but definitely there is a difference in measurement, right? So let's say there is a slight, change in measurement. Okay. So the source term is same. This is f in omega, but the data which you are going to get on the boundary, that is different. So let's say this g is getting transferred to g, let's say epsilon. Okay, on the boundary. So let's say we call it a u epsilon. Okay, so this is an epsilon perturbation. Yeah, let's say you solve this problem 1, 2. Let u and u epsilon solve 1 and 2 respectively. So what am I saying? I am saying that both u and epsilon solve the same problem in omega. Laplacian, so they satisfy minus Laplacian u equals to f minus Laplacian u equals to f. U and u epsilon both satisfy the same equation, right? But on the boundary, u is g and u epsilon is g epsilon on the boundary. That's the difference. So g epsilon can be, for example, you can think of g epsilon to be, this is for an example, it can be else also. Something else. So think of this as g plus epsilon, something like this. So basically, you are just taking a small perturbation. This is, think of physically as the error in computation. Think of this as error in computation. Okay. So basically, you have this respectively, such that now this error, you see, you are measuring the same thing, but it may happen that the measurement is slightly off, right? So basically, the difference between g epsilon and g is very small. So such that the maximum, okay, of g minus g epsilon, okay, let's say that is less than epsilon. So we choose epsilon positive. Let's say that is given to you. So the maximum and x is on del omega. So for if you take the maximum of g minus g epsilon, Yeah, let's say that is very small. So basically what am I doing? I am assuming that while doing this, measurement on the boundary, the error is extremely small. So basically the difference between G and G epsilon, yeah, for every X, the maximum of that is always bounded by epsilon. Yeah, we are assuming this thing. Now let's say phi, you are defining it by U minus U epsilon. Okay, clearly minus Laplacian of phi is 0 in omega. Okay, and phi is equals to G minus G epsilon on the boundary. Okay, so you see what this gives you is the following: U of x, it means that the U, so by from Maxwell's principle, if this happens, see, C is a harmonic function, right? So therefore, since C is harmonic in omega, then strong Maxwell principle implies phi of x. Okay, this, so you see what I am trying to say is this is always less than equal the maximum of phi on the boundary for all x in omega bar. Yes, yeah, that's the maximum principle, right? So it says that the maximum is attained on the boundary. That will imply that phi of x, so mod phi of x, I can say this thing, right, is less than equal maximum of mod phi over del omega, right? I can say this. Yeah, so you see what will happen is this: mod phi of x is essentially U minus U epsilon. Okay, this is less than equal maximum of del omega. Mod phi is G minus G epsilon. So basically phi is G minus G epsilon on the boundary. So I'm just replacing with this, and this is given to be less than epsilon. Okay, so you see what this says is this: if you change the initial data on the boundary a little bit, the change in the solution is also going to be, bounded by that similar error, right? So that implies that the maximum of mod U minus U epsilon, okay, and over omega bar, this is less than epsilon. Okay, so hence, what does it say? For, let me put it this way: for small change in boundary data, okay, the change in solution, in this sense, that the maximum of U minus epsilon, okay, change in solution is also small. Okay, more precisely, it is bounded by the error is this epsilon error in the boundary data, right? The boundary data. I hope this is fine. Yeah, you have understood. So what it is saying is this: if you change your boundary data a little bit, let's say, and the change is given by the maximum of G minus G epsilon is less than epsilon. If that happens, then your initial, the solution U minus U epsilon, what is the change in the solution? That change is also bounded by epsilon. Yeah. Okay. So little change in the boundary data also changes the solution a little. So that is expected. Yeah. So you see, by doing this uniqueness theorem and this stability and the perturbation, we have actually did two things. So here we proved that Laplacian U equals to F in omega, U equals to G on the boundary. Okay, for this equation, let's say that is 1. So uniqueness and stability under perturbation holds. Okay, so we have proved it. So we proved this particular thing for this equation. Okay, for this equation. Now the question is this. So do you think that one is well posed? Okay. So if you remember, what are the properties of well posedness? First of all, you have to show that the existence, uniqueness, and then the stability. Yeah, we have proved the uniqueness and stability, but we didn't prove existence. So essentially, the only thing left to do is to find the existence. Okay, and this is the difficult question in this case, and this we will do it in the next week. But this week we will continue to talk about more properties of harmonic function. Yes. So with this we are going to end this particular lecture.